Hey friends, so today begins a new unit. This one's kind of a long unit. It's on functions in general, but it's kind of divided into three sections. Okay, this first section we're going to talk about radical and rational functions, and then the second section we're going to talk about polynomial functions, and then the third section we're going to talk about function operations. So we're going to look at adding, subtracting, multiplying, dividing, composing one function in another. Okay, so with those three sections, we're going to have kind of like a quiz at the end of each section. So you'll have radicals and rationals and then a quiz, polynomials and then a quiz, and then function ops and then a quiz. Okay, most important question that we want to ask today is you need to take a look at this picture. Hopefully I'm not covering it too much when the video appears. The three types of people in math class. You need to identify which person are you. Okay. So I'm hoping today is going to feel really, really familiar, okay? Because we just came off of a unit on transformations where we talked about, you know, what does A do? What does B do? What does H do? What does K do? And that's all we're going to do today, really, except we're going to put it in the context of a radical, okay? So you know that a radical, y equals the root of x, okay, would look like this, okay? Starts at 0, 0, then it has 1, 1, then it has 4, 2, and 9, 3. Okay, you could get some friendly points. When you're sketching a graph, always give me some friendly points, okay? Don't just give me a quick little picture. You'll always be given some sort of a grid, so make sure you have a few accurate points there. Okay, so what we're going to do is we're going to introduce the concept of y equals a b x minus h plus k. Okay, well, your a, b, h, and k do the same thing they've always done. We're just now looking at it in the context of a radical graph. Okay, so this first section here, just take note of this little picture here. When you see that little picture, it's not in your workbook, so don't try and find it in your workbook right now. It's just me kind of talking, me kind of introducing things. An expression in the form, the nth root of x, where n is any number I want, any real number that I want, is called a radical, okay? The kind of check mark symbol, the symbol for that is called the radical sign, n is called the root index, and x is the radicand. Now, recall that a square root, the root of x, is only defined when the values of the radicand are, and you'd be yelling at me right now, greater than or equal to 0, or maybe you just said positive, and that would make sense as well, okay? So if I was going to determine the values of x when the root of 3x minus 4 is defined, I need to make sure that my radicand is positive. So it's not about x being positive, it's about the radicand itself, the thing that's underneath the square root being positive. So what I do is I set that greater than or equal to 0, and I solve for x, okay? So if I do that, 3x minus 4 is greater than or equal to 0, I bring my 4 over, divide by 3, and I get x is greater than or equal to 4 over 3. Now, you did a lot of that in 20-1, okay? So this should feel pretty familiar. This should feel pretty okay. The big difference between 20-1 and 30-1 is we connect all the number stuff that you did in 20-1 to the visual aspect in 30-1. Okay, and what I want you to understand is those restrictions on a radical graph actually become the domain of the graph. Okay, if you were to grab your graphing calculator, and you got lots of time, you're sitting home doing nothing, go ahead, grab your graphing calculator and put that into y1, the root of 3x minus 4. Okay, and what you'll notice is this graph starts at 4 over 3 and heads to the right instead of starting at 0 and heading to the right. Okay, all right. Awesome. So radical functions are functions where one of the variables is in the radicand and can be written in the form a, the root of b, x minus h plus k. The characteristics are very different from that of other polynomials, partly because we have a start and a stop here. Sorry, we have a start, but no stop here, right? This guy here is my starting point or my end point, sometimes you'll hear it called. Whereas a polynomial, it's continuous all the way from infinity to negative infinity to positive infinity. So in polynomials, the domain was always x, the number of the reals. But in radicals, we end up having a start and then an end of some sort. Sorry, I did it again. A start, but then no end. Okay. Okay. So what we're going to do here is we're going to start filling in the table that's in your book. This is our base function first, and I've shown it to you on the graph. Y equals, or f of x equals the root of x. So there are no descriptions to describe at the moment because nothing's there except the base function. So the image point is just xy. I haven't done anything to it. The restrictions would be x is greater than or equal to 0, and that becomes the domain. So the domain is all the values of x such that x is greater than or equal to 0. In interval notation, be 0 to infinity. I can be 0, so I have the square brackets. I can't be infinity, so I have the curved brackets. And my range is the same thing, 0 to infinity. So now the first transformation that I do with it is I'm taking a look at the root of x minus 2. Now, if you're comparing all of these with your graphing calculator, I would keep the root of x in y1 and then put this guy in y2 so that you can compare, okay, what happened to my original? Where did my original end up? But I want you to be able to look at this equation and take a really solid guess that it should be moving 2 to the right. Because anytime I replace x with x minus 2, with every function that we did in the last unit, it moved 2 to the right. So this one's no different, right? I've replaced x with x minus 2, I'm moving 2 to the right. So that's a horizontal translation, 2 units to the right. My image point then will be xy maps to x plus 2, comma y. I moved it 2 to the right. My restrictions will now be x is greater than or equal to 2, which also becomes the domain. So now my domain will be 2 to infinity instead of 0 to infinity. And the range won't change because I didn't move it up or down, right? If I do a horizontal item, it shouldn't affect a vertical item. So my range stays the same as 0 to infinity, okay? All right, and then there's the picture. I can see that the red graph has been moved 2 units to the right of the blue graph. Okay, next guy is the root of x minus 3. Now, just be careful, since we're talking about this, when you communicate stuff to me on a test, you need to make sure you communicate clearly. So I need to see exactly where that root ends. Okay, I don't want to be looking at that root halfway over the negative and then thinking, okay, well, did they really mean it was x minus 3 under the root and they stopped too soon? Or did they mean it was x under the root and they went too long? So make sure you're very clear as to where that root ends, okay? It's all about communication. Math is a beautiful language. Okay, so what am I doing here? That's a vertical translation, 3 units down. Sorry, I have no mouse, just a sec. Vertical translation, 3 units down. The image point then would be x comma y maps to x comma y minus 3. The restrictions are still actually going to be greater than or equal to 0. I haven't moved it left or right, so that hasn't changed. So my domain hasn't changed here, but my range has. My range is now going to go from -3 up instead of from 0 up because I shifted the whole thing down. Okay? Awesome. Okay, and then there's the graph. You can see the red guy is shifted 3 units down. Okay, so now I have a stretch involved here. My stretch is 1 over 4 because that's a b value. That's a horizontal stretch of 1 over 4 about the y-axis. So now my image point is going to be x comma y maps to 1 over 4 x comma y. Now my restrictions. In this particular graph, the horizontal translation actually doesn't affect my starting point only because my starting point is 0, 0, right? If I'm multiplying 0 by a quarter, it's still going to end up at 0. Okay, now you got to be careful with that because say my starting point was here at -4. Say that was my graph. Okay, so my starting point was at -4, 0. Then I would definitely have a new starting point, right? My new starting point would be at -1, 0 because -4 times a fourth is -1. You are still multiplying everything by a quarter. It's just that this guy's a little special because the first x value is 0. The stretch won't affect the starting point here because 0 times anything is 0. Okay, so my restrictions remain the same as x is greater than or equal to 0. My domain hasn't changed and my range hasn't changed. Okay, so now when I graph this, I can use the help of my graphing calculator or I can get some friendly points, right? I know 0, 0 will remain as 0, 0. I know 1, 1 exists. Well, that will become 1/4 1, so I can back that up to 1/4. Okay, I know the point 4, 2 exists, so that can back up to 1, 2. And you can see that this is going to rise above the original graph just based on those 3 points, right? So it ends up looking like this. And that kind of makes sense. If I take like godlike hands on this graph and go, it's going to crumple everything so that it's growing quicker, right? Okay. Next guy, we have a vertical stretch of 2. So a vertical stretch by a factor of 2 about the x-axis. The image point would be xy maps to x comma 2y. The restrictions actually, again, are the same. Again, just for the same conversation we had last time, my starting point is going to remain the same, only because the y value of my starting point is 0, and 2 times 0 is still 0. The x hasn't changed at all because I've done a vertical item, so there's no reason for the restrictions to change if I'm changing y stuff. Okay, so x is greater than or equal to 0. The domain would be x is a member of the reals, or 0 to infinity. The range would also be 0 to infinity. Okay, and now the graph, again, we could look up nice pretty points. 0, 0 will stay as 0, 0. The point 1, 1 would become the point 1, 2. My other friendly point was over here on 4, 2 would become 4, 4. Okay, so you can see that this is actually going to rise kind of a steeper guy than the other one. Okay, actually, it's not any steeper. So this is a great time to have a quick little conversation. I want you to notice, stay with me, we're going to do something really exciting, okay? I want you to take a look at this graph, okay? Everybody stare at this graph, and I'm going to go back one and look at that graph. And I want you to look at that and say, huh, that looks like the same graph. Okay, here it is again. And then I'm going to go forward. And there it is. It's the same graph. Now, why is it the same graph? Let's talk about that because that's fun. Okay, so we have, I gave you y equals the root of 4x the first time, and I gave you y equals 2 root x the second time. Okay, so this one was a horizontal stretch of 1/4 according to my transformational stuff. This one was a vertical stretch of 2. But what I want you to see is mathematically, these guys are the exact same thing because the root of 4 is 2. I can take the 4 out and make it a 2, okay? Radical graphs are special like my mom told me I was. The a and the b value can actually be interchanged depending on whether you just want mathematically the number out of the square root or the number in the square root, okay? What can't change is when I have a reflection, wherever that reflection is, that has to stay. So say I had both a vertical and a horizontal reflection, I'd have to have a negative out here and I'd have to have a negative in here, but the number itself, without the negative sign, could come in and out, okay? And that's going to be actually a really helpful principle in a minute when we go to try and build equations from pictures, okay? Which we'll be doing in just a sec. All right, so we're going to do a quick summary. You guys at this point could probably do this in your sleep because I've drilled you and drilled you and drilled you about what A means and what B means and what H means and what K means. So just take some quick notes, make sure you're comfy with it. How does the A value affect the shape of the graph? Well, it's a vertical stretch by a factor of A about the x-axis. What would happen if it was less than 0? That would be a vertical reflection, also about the x-axis. A reminder, when you're describing these things to me, you do need to say about the x-axis, because it could have been about any line we want. Okay, how does the b value affect the shape of the graph? It'd be a horizontal stretch by a factor of 1 over b, and that would be about the y-axis. And again, if the b value is less than 0, if it's negative, we say that that's a reflection. Okay, horizontal reflection about the y-axis. H and K, H gives me my horizontal translation. If H is positive, I'm going to the right. If H is negative, I'm going to the left. Always think, what's the value of H? And it's x minus whatever that value of H is. K is the vertical translation. If K is positive, I'm going up. And if K is negative, I'm going down. Okay. Hints, know where your vertex is. Now, really, that should say endpoint. I like endpoint better than vertex there. Know where your endpoint is, okay? Just that starting point. The vertex is where we change direction. Reflections change your domain and range. So that's another important thing. Okay, if I had given you, say, the root of x, so it looks like this, okay? As soon as I say root of negative x, that would now look like this, right? So now my domain becomes x is less than instead of x is greater than. If I had given you a vertical translation, now y is less than instead of y is greater than, okay? And then this guy, if I had given you both a vertical reflection and a horizontal reflection, I would end up right here, and that would be x is less than and y is less than, okay? So those reflections change the way your domain is looked at. So if you're doing it in set builder notation, it changes it from a greater than to a less than. If you're doing it in interval notation, it'll change it from a comment that says something like 2 to infinity to a comment that says negative infinity to 2. So just be careful of that, okay? Okay. So now what we want to do is read the transformations. So here's an equation. You want to clean this up first. You want to write it as y equals first. The other thing I want you to kind of see right away is this is not in factored form. So I would want you to say, okay, I have to take out that negative. So that'll be x plus 2 here. And that actually changes what my my horizontal translation is. So you want to be super, super careful of that, okay? So description of the transformations, you should give me 3 of them. I assume you brought that plus 3 over. And so that would be, we'd have a horizontal reflection about the y-axis, and then we'd have a horizontal translation 2 to the left and a vertical translation 3 down. Okay, the domain then, see if you can do this without a calculator. Now, nobody's taking your calculator away from you, but just try, see if you can do it. I have a reflection, so now I'm gonna be less than. Then I moved left 2. So instead of being less than 0, now I'm gonna be less than negative 2. So as set builder notation, I'd say all the values of x such that x is less than or equal to negative 2. Interval notation, I'd say negative infinity up to negative 2. Okay, the image point, sorry, I forgot the image point. I got so excited about the domain. X comma y maps to negative x minus 2 comma y minus 3. And then the domain I just talked about, negative infinity to negative 2. The range, I'm greater than 0, and then I moved it down 3, so now it'll be greater than negative 3, so it'd be negative 3 to infinity. Okay. So the next question we're going to try is negative y plus 3 equals negative the root of 2x plus 2. Now, there's so many things that I want to pop into your head right now. Number one, I want you to look underneath the square root sign. I want you to see that that radicand is not fully factored, okay? Remember that the 2 has to come out. And the reason the 2 has to come out is because when we're doing transformations, those 2 transformations involve 2 replacements, right? We talked about this in the previous unit. If I'm doing that horizontal stretch of a half, I replace x with 2x. Then if I'm going to go left however many units I'm going, which you're going to tell me that in a second, I have to replace x again, but there's already a 2 there, so that's where that double set of brackets comes. So if you don't see the double set of brackets, you have to rearrange it so that you see the double set of brackets, which means the 2 has to come out. So it'll be 2 bracket x plus 1. That's actually only going to go to the left 1. Okay. Okay, then I got some other funny business happening. You want to bring that 3 over here. Okay, so that'll be negative 3. But then you also have to divide by negative 1 essentially so that you get rid of the y. Now, you got to be careful with that. If you divide by negative 1, every term has to get divided. So this all together is 1 term, but so is this. Lots of kids forget this one, okay, because it's sitting over there on the other side. Every term has to get multiplied by negative 1. So your final kind of simplified form of this will be y equals the root of 2 bracket x plus 1 plus 3. Now we're ready to actually read the transformations. There'd be 1, 2, 3 statements you want to make. Pause me and write them down yourself. So your description of transformations would be a horizontal stretch of 1/2 about the y-axis. You've got a horizontal translation 1 left. because of the x plus 1, and then you've got a vertical translation 3 up. Okay, so the image point would be x comma y maps to, we've got 1/2 x and then minus 1, and then y plus 3. Your domain, well, remember, because my starting point's at 0, 0 right now, when I start at 1/2, or when I multiply by 1/2, that doesn't change the starting, that starting 0, 0. But I've gone to the left one, so now it's going to be greater than -1. So it'll be -1 to infinity. And then my range, I've started at 0, but then I've gone up 3. When I say I start at 0, I'm talking about the base function, just for clarification. I'm looking at that root of x, and then I'm comparing what I'm doing to root of x. Okay, so then the domain would end up being -1 to infinity, and the range would be 3 to infinity. Okay. All right, this one's not in your book, but again, I've given you questions like this before, and it's just a matter of making sure you can see the visual. So which picture matches with which transformation? The blue graphs are always the original. The blue graphs are the y equals the root of x. So here I have a horizontal reflection. So if I have a horizontal reflection, do that in your head, and that's going to be graph 4. Okay, here I have both a horizontal reflection and a vertical reflection. So I'm going to flip it vertically and flip it horizontally. So if I do that, that would end up being graph 1. Here, that's just a vertical reflection. So that would end up being graph 3. And then the final one, that's a diagonal reflection against the line y equals x, which would be like that line right there on the graph. And so that would be graph 2. Okay. All right, back to your book. We're going to determine the equation. Now, we've already talked about the fact that a and b are interchangeable. So you'll notice in this one, we actually just said, we just gave you an a, okay? So write it in terms of a, not b. So you have an endpoint. You know that your endpoint here is -3, 2. And then go for another friendly point. And usually as math teachers, we'll always give you a friendly point because we don't want you guessing. Like we don't want you looking at this point right here and saying, huh, that looks like -1, 3.5. Well, maybe it's not, maybe it's 3.4, right? So then that throws everything off. So use the friendly point we gave you. The friendly point we gave you here was this guy, 1, 4. It says determine. So you need to plug in your h and k from your endpoint. And then you're going to use that friendly point to plug in for x and y, and then you can solve for a, okay? So I've plugged in my -3 and 2 for my endpoints. Now I'm going to plug in the 1, 4. So y is 4 and x is 1. Now I've got the root of 1 plus 3, which is 4, and the root of 4 is 2. Bring the 2 over and divide by 2, and I get a is 1. Now, it's always nice when we get to come to a conclusion that says a equals this, but remember, that's not the answer. The answer is to determine the equation. What you just did was algebraically solve for a, which you have to do, but now you have to answer the question. And the question is, what's the equation? So the equation is the root of x plus 3 and then plus 2. And again, make sure your square root is chopped off right there. I don't want there to be any confusion as to where your square root ends, okay? Be very, very clear in your communication. Okay, try this one. Now you should look at this one and say, hey, I'm gonna have a negative a value here because I see, like if we just talk orientation right now, I see that this graph has been flipped vertically, okay? Now, that doesn't mean you put a negative in. That means when you do the math, when you solve it for a should come out to be negative. And if it doesn't, that's kind of a check and balance to make sure you go back and see where you went wrong, okay? So I got -3, 2 as my endpoint again. This time my friendly point is 1, -2. So I'm gonna plug all that information in here. I've got 1 plus 3 again, which is root of 4. Root of 4 is 2, so I'm looking at negative. I also brought my 2 over there. So -4 equals 2a. And then when I divide by 2, I get a equals -2. So the equation for this guy will be x and y come back in, and then you need to tell me what a, what h, and what k is. So y equals -2 root of x plus 3, and then plus 2. So what if I wanted to do a b value here? what you have to realize is I can put this 2 in. Okay, if I put the 2 in, it would have to become the root of 4. And then that would be the same thing. But you have to be careful. You can't touch that negative sign. You can't bring a negative sign in. So it would just be negative root of 4 bracket x plus 3 like this. Okay? Good. All right, determine the domain. Well, if I'm determining the domain, we talked about the fact that the restrictions on the radical become the domain of the graph. So all we have to do is take a look at the radicand. We're going to set it equal to 0 and solve. Sorry, I said set it equal to 0. I meant greater than or equal to 0. Okay, so bring the 9 over, divide by 3, and we get x is greater than or equal to 3. So in set notation, that would be all the values of x such that x is greater than or equal to 3, comma, x is a member of the reals. Or in interval notation, that would be square bracket 3, comma, infinity, curved bracket. Okay. Make sure you're listing the word domain. If you are going to tell me the domain, I need to know that you know what you're talking about. Okay. Okay, try this one. Again, we're looking at negative 7x plus 12. We want to set negative 7x plus 12 greater than or equal to 0. We'll bring that 12 over, so we get negative 7x is greater than or equal to negative 12. Now, at this point, you have to divide by negative 7. I got to take you back to grade 9. Just review some grade 9 algebra rules for a second. When you divide by negative, your inequality has to flip. Okay, so this is going to end up being x is, this was greater than, so now it'll be less than, and then it ends up being 12 over 7. Okay, so your domain on this one is now x is less than 12 over 7, where x is a member of the reals. And that should make sense to you because we've already talked about the fact that that is a horizontal reflection. Well, if it's a horizontal reflection, I've gone from a greater than domain to a less than domain like this, right? That's what a horizontal reflection would do. So it makes sense that the inequality flips on me. Okay, all right. So we'll just quickly summarize here. All radicals can be written in the form y equals a root of b x minus h plus k. The value, the a value, is the vertical stretch factor of both the x-axis, or if you'd rather, you can say the line y equals 0, by a factor of a. If a is less than 0, a vertical reflection has occurred, and that will be about the line y equals 0, or again, you can say the x-axis there. The b value is the horizontal stretch factor about the y-axis, or you can call it the line x equals 0 by a factor of 1 over b. It's always the reciprocal. The stretch factor is always the reciprocal of b. If b is less than 0, we have a horizontal reflection against the line x equals 0, or if you prefer the y-axis, that's totally fine as well. The h value is the horizontal translation. The k value is the vertical translation. Values underneath the radical must be greater than or equal to 0. And then to determine the domain, you can either think of where the function has been transformed, or just set whatever is underneath the radical to be greater than or equal to 0. Okay, all right, so you're gonna do this guy for practice. Make sure you're going through it, make sure you're really clear on your communication, and as always, come see me if you have any questions, okay? Tomorrow we will look at rational functions. All right, take care, guys.